In example 1.17d, we're going to see a lot of similarity to part B, where we have a radical symbol. This is a square root, and the expression 9 minus x squared is underneath that square root. And the idea here is that we never want to see anything negative appear underneath the radical. So to keep that from happening, we're going to take that expression 9 minus x squared, and we're going to set it to be greater than or equal to 0. And that will do exactly what we want. That'll keep any negative values from being in there. Now, with this, I would then add x squared to both sides, giving me 9 is greater than or equal to x squared. And this is a little different from part B because I have x squared and not just x by itself. So this is actually going to be translated into a compound inequality. And this particular compound inequality will now be simplified into the following. Negative 3 less than or equal to x less than or equal to positive 3. Now some of you might look at that and say, okay, if I was to take the square root of 9, that's how I would end up with 3. And that certainly is correct, but you would also have the ability to have a negative 3 in there as well. So that's where I end up getting the two boundaries of positive 3 and negative 3. And by looking at the original inequality that's here in between the 9 and the x squared, that's what allows me to then be able to turn it into this compound inequality right here. So the compound inequality is really expressed here, but it's the line above that initiates that process. So from the number line perspective, negative 3 and positive 3, I should have a closed boundary at negative 3 and positive 3, and I'm looking to keep everything in between. So the domain for G, square bracket negative 3 to positive 3 with a square bracket. So there's your domain. Now let's define the function. Function name is G. First set is the domain. That's what maps to the real number set given by the equation g of x equals the square root of 9 minus x squared.